Thank you, Pierre. It's a pleasure to be here. I'm not going to thank the organizers because I would be included. But anyway, it's a pleasure to be here in this geometric analysis event. So I'm going to talk about curvature flows and scalar curvature problems. Scalar curvature problems. And the idea here is to sort of advertise that there are several problems in geometry related to scalar curvature and minimal surfaces, which actually can be solved as applications of curvature flows. So I'm trying to, along this mini course, to give at least 3 examples of such flows and their applications to geometry. So the first example of application is the Riemannian Penrose inequality. Which I'll be talking about today. This is something which has its sources in general relativity and has more than one proof. One of the proofs is due to Huisken and Eilman and uses the inverse mean curvature flow. That's the proof I'm going to talk about today. So the second example is related to computing the Yamabe invariant of RP3. So the Yamabe invariant here is a little different from the Yamabe invariant defined by Zindin. Zindin only considered the conformal class. So after you define the invariants for the conformal class, you can take the sup over all conformal classes. That's the invariant that I'm talking about here. It's a topological invariant of a manifold. And Bray and Neves computed these invariant for RP3 using, again, the inverse mean curvature flow. So it's a general, it's an open question. Actually, there's a conjecture due to Ricci that predicts the Riemann invariance of all the spherical quotients, but the only one known so far is RP3, right, due to the inverse mean curvature flow. So it's a very nice proof which combines flows, minimal surfaces, and the Yamabe problem. And finally, so this is more or less the how I'm going to divide my talks. In the third talk, I'll say a few things about rigidity problems. Let me put it this way: rigidity of area minimizing surfaces. Minimizing surfaces. And I'm going to talk about, because it's related to that, something that I was involved in the Minus conjecture. So I'm going to talk about some rigidity results, and in the end, a non-rigidity result, which is a counterexample to the conjecture of Minus. So that's more or less the scheme of the talk. So again, I won't be very technical. I could have concentrated the whole mini course in the first topic here, because the proof involves a lot of regularity theory, and it's quite involved. So I chose to not to concentrate in the technical aspects, but to try to give a general idea. What are the main ideas of the proof, and what sort of mathematics is involved? And in that way, I can give a general. I can give more than one example of application. Okay, so right. So I'm going to talk about the Riemannian-Penrose inequality now. So the basic definition. So the object that we are interested in is called asymptotically flat manifold. Let me give a definition. You say that a manifold M3G, let's say complete, is asymptotically flat. Asymptotically flat. If there exists a compact set K contained in M, such that the complement M minus K is diffeomorphic to a complement of, let's say, the unit ball in R3 to R3 minus the unit ball. And we can use this diffeomorphism to put coordinates in M minus K, so that in these coordinates, I want the metric to be, to converge to the flat metric in a controlled way. So I'm going to assume the Gij. So these are the components of the Riemannian metric. This is going to be equal to delta Ij plus order of 1 over norm of x. I want the first derivatives to go to 0 with order 1 over x squared. And I want the second derivatives to go to 0 with order 1 of x cubed. All of this as x goes to infinity. Okay, actually in the literature one can find more flexible definitions of asymptotically flat manifolds, and in some proofs one can actually work with more general definitions and reduce the proof to the case of this set. And so this is sort of like the important, the most natural conditions that one can ask for the asymptotically flat manifold. So O of big X, of course, means something that is bounded by a constant times 1 over X in absolute value. So the picture would be something like this. Let's see, I'm going to draw it like this. And here you might have some topology. So there is a compact set K such that outside K the manifold is just R3 minus the ball, and the metric looks asymptotically flat. This is more and more flat. So these are the manifolds we will be concerned with in the first talk. And they sort of come from general relativity, right? In general relativity, you look at the Einstein equations in 4-dimensional space-time, which is supposed to be a Lorentzian metric. So these manifolds, these are, I'm going to concentrate in 3 dimensions. They're supposed to be space-like slices in this Lorentzian space-time. And the idea is that, so this is going to model a gravitational system, an isolated gravitational system. The idea is that if the matter of the universe is sort of concentrated in a compact set, so the metric measures the gravitational field. So the idea is that as you go to infinity, the gravitational field should be weaker and weaker. So this is what we model by the fact that the metric is asymptotically flat. So these are important models in general relativity. Okay, and an important definition, so an important discovery actually, due to 3 physicists, Arnowit, Deser, and Misner. They discovered that these manifolds come with a good definition of mass. So defining a mass is sort of immediate in Newtonian physics, right? You just integrate the mass density. But in general relativity, it's actually a complicated problem. There are lots of papers dealing with the problem of having a good definition of mass for compact domains, let's say. But in the 60s, so this is the 60s, these 3 guys discovered that there is a nice quantity which represents the mass of the whole thing. So it's difficult to define mass for compact sets, but there is a good definition of mass for the whole universe. So that's called the ADM mass. The definition is, so assume, first of all, I have to assume that the scalar curvature is integrable. This holds. This is, seems a little technical, but it's not actually. Most of the natural examples will be scalar flat. So they set as this immediately. So the mass, or the ADM mass of the manifold, is defined to be, let's say, of M is defined to be the flux integral, well, the limit of the integrals. So the idea is that the mass is going to be, well, these manifolds come with a natural, well, not a natural, but they come with coordinates around infinity. So you choose one of these systems of coordinates, and then you define what's the constant. I always forget. So the physicists like the constants, right? So for us, it's not that important, but let me put it 1 over 16 pi. The limit, well, the integral of the boundary of dr of 0, the sum in I j, and I guess this is the trace, right? So you get dj g I minus di g ij nu j over the surface, the sigma r, where here I can take nu to be just the, let me put it like an n. N is just the normal vector, Euclidean normal vector. So this is the Euclidean normal vector, this is the Euclidean volume element. It's easy to prove that if you put the Riemannian normal or the Riemannian volume element, the result will be the same because of the asymptotics. But let's put it this way. This is all Euclidean, of course, with the metric G here. So you take, so what's going on is that you look at infinity, you choose this large ball, which is contained in the complement of the compact set K. You compute this flux integral, and you take the limit. So it is possible to prove that this number doesn't depend on the coordinates you choose. So this is actually a geometric invariant of the manifold. This is a geometric invariant. So you really need the scalar curvature to be integrable so that this is well defined. There's a sort of integration by parts that you can do, and the integral of scalar curvature appears naturally in that computation. So the basic example here, of course, the trivial example is the Euclidean space with the Euclidean metric. It's obviously asymptotically flat, and the coefficients of the metric can be chosen to be constants, so the mass here is just 0. Right? So the Euclidean space has 0 mass. Okay, then in the 70s, people sort of tried to prove that this number has to be non-negative, right? So if this is supposed to be a mass, the first thing you need to check is that it's a positive number. Right, so this became known as the positive mass conjecture, which now is a theorem that I'm going to state. So the positive mass theorem. So this theorem was proven originally by Shen and Yao in '79, and later there's another proof just 2 years later due to Witten. So the theorem says the following. Suppose we are in these conditions, right? So let M3 be asymptotically flat. So I'm going to abbreviate as AF with scalar curvature integrable. Then if the scalar curvature is non-negative everywhere, then the mass, the ADM mass, let me put it this way, is non-negative. Inequality mass equal to 0 only if your manifold is isometric to Euclidean space. Right? So this theorem says that the mass is really a non-negative number and can only be zero when your manifold is isometric to the Euclidean space. So, so this condition of non-negative scalar curvature appears very naturally in general relativity. So in general relativity, again, you work with four-dimensional spacetimes which obey the Einstein equations. And there is a physical condition called the dominant energy condition that you assumed on your spacetime, that when restricted to a hypersurface of, let's say, mean curvature 0 in that space, implies that the scalar curvature is non-negative. Okay, so you expect that the so-called maximal space-likes in relativity have non-negative scalar curvature. So it's sort of like saying that the energy density is non-negative. Okay, that's a very famous theorem. Let me say that this definition also works in higher dimensions, right? You can forget about n. You can put n here, and instead of 1, you would put, for example, the natural power is n minus 2, right? So you can talk about these things in higher dimensions, and actually, this theorem is known to be true for dimensions less than or equal to 7. In general, this was proven using minimal surfaces, minimal hypersurfaces, by Shen and Yao. And for any dimension, it is known to be true in the spin case, which is a topological condition on your manifold. So this uses spinors, and that's the proof of Witten. So the remark here is that the general positive mass theorem is completely open. Well, maybe the completely here is not really fair because there are some people working on it, but so far it's been 30 years and there's no proof of this for outside the spin case. So this is a totally open question. Okay, so the positive mass theorem implies, it can be seen as a rigidity statement for the Euclidean space. A very simple corollary, which actually will be important for my next talks, is that if you have a manifold such that, if you have M3G, right, such that outside a compact set, there exists a compact set with outside the compact set, so you can suppose the manifold is isometric, right, to R3 minus a ball, for example, and suppose that the scalar curvature is non-negative, then the manifold has to be isometric. The whole thing has to be the Euclidean space. So in other words, if you take the Euclidean space and try to perturb it in a compact set, well, you cannot do it so that the scalar curvature is positive, right? Any perturbation of this with non-negative scalar curvature has to be actually isometric to the original Euclidean space. So this is an example of rigidity result, which will be the subject of this mini course in the next talks. Okay, so the positive mass theorem is the natural statement if you think of the Euclidean space. The Euclidean space here is the model. But there's another model which is very important to relativity, and that's called the Schwarzschild manifold. So the other example, natural example in this setting, is the example of the Schwarzschild manifold. So this is just, you take R3 minus the origin as the manifold, and the metric here will be a conformal deformation of the Euclidean metric. the definition is 1 plus m divided by 2 norm of x to the power 4 times delta, where m here is chosen to be a, let's say, a positive number. Right. So that's the definition of the metric. It makes sense on R3 minus the origin. You can see that it is complete in both ends. So if you try to draw a picture of this, you see that this manifold is actually symmetric with respect to a minimal surface. It sort of looks like a catenoid. The picture would be something like this. So here you have an asymptotically flat end. Let's see. Right. These are asymptotically flat ends. And here there's a minimal surface, which is the boundary of the ball of radius m/2. So if you look at this, these coordinates, you look at the sphere of radius m/2, this is a minimal surface, and actually this is an area minimizing. Area minimizing surface. When I say area minimizing, I refer to the homology class. Right. And you can actually very easily compute the area, right, because the metric is just conformal to the Euclidean space. So when the radius is m/2, you get 1 here plus 1, 2. To the power 4, you get 16, right? So the area is 16 times, is that correct? 16 times the area with respect to the Euclidean metric, right? But the area with respect to the Euclidean metric is pi times the square of the radius. Well, 4 pi, right? There's a 4 here. So if you do this calculation, you get that the area is 16 pi m square, right? So the area of this minimal surface is related very nicely to the mass the manifold by this relation, right? The bigger the mass, the bigger the area of the minimal surface. So that's the model, and actually one can use the formulas of the previous talk by Zindin, right? The only difference is that my Laplacian is different. But you can compute since this is a conformal metric, right? This is the conformal deformation of the Euclidean metric. You can compute the scalar curvature. Now, let me just put it this way. The important fact is that the function 1 plus m divided by 2 norm of x is harmonic in R3. Right. And of course, the scalar curvature of the Euclidean metric is 0. So if you put these two facts together with the formula written down here by Zindin, you get the scalar curvature of G is 0. So this is actually a scalar flat manifold. So it's a very nice manifold. You can prove that it's the only scalar flat rotationally symmetric example, right? As you do for the catenoid. Okay, so we're getting close to the flows here. So that's the model. And in the 70s, Penrose, that's 73. So minimal surfaces also play a role in relativity because they're sort of related to the notion of horizons, right? So, if I don't know much about physics, but you can think of them as black holes, the surface which encloses a black hole. And the idea is that black holes, if they exist, they should contribute to the mass. So using a lot of physical reasoning, Penrose came to the following conjecture. He conjectured that if you have an asymptotically flat manifold, well, and all that, his conjecture was that if n is minimal, I'm going to state precisely what. Let me just put it briefly here. There's a precise notion of it needs to be more than minimal. But anyway, the conjecture is that the mass should be at least the square root of the area divided by 16 pi. you can see here that in the case of the Schwarzschild manifold, you get exactly the equality case. Right? You divide by 16 pi, take the square root, you get the mass. So this was the conjecture. And so he devised this as, so he used a lot of physical arguments. One of them was what's called the cosmic censorship conjecture, which roughly says that generically, if the space-time develops singularities, generically you should expect that these singularities are surrounded by a horizon. Right? And he devised the Penrose conjecture as a test for such conjecture, which is, of course, it's open, it's much harder. But the good thing is that it is actually now, 10 years ago, it was solved, and it's actually, there's a precise formulation which solved the problem. So I'm going to talk about the Riemannian case, as I said in the beginning. There's a little bit of, controversy of whether one should expect a Lorentzian version or not. I should say that the positive mass theorem has a version for space-times, which was proven by Shen and Yao, but the space-time version for the Penrose conjecture is still missing. So let me state the Penrose inequality here. So the theorem. Penrose inequality says the following. Right, so suppose M3G. I'm going to think my model will be the half Schwarzschild. So let me just put this yellow here. I'm going to forget about the other half. So this will be the half Schwarzschild. Okay, so suppose that M3G is complete asymptotically flat, and suppose, of course, that the scalar curvature is bounded, is integral. So I'm going to assume that the boundary is non-empty here, right? And assume then that the boundary of M is a compact minimal surface. Compact minimal surface, which could be possibly disconnected. Possibly disconnected. Such that M contains no other minimal surface. So as I said, it's not enough to be a minimal surface. You need the region to be such that there are no others, right? In the Schwarzschild, for example, these leaves have positive mean curvature, so you can easily see by the maximum principle that there are no other minimal surfaces inside this region. So that's an assumption for the Penrose inequality, and I'm going to explain why this is needed. Okay, then the mass is at least the square root of area divided by 16 pi, where A here is the area of the boundary. Sorry, here I have to, it's not really the area of the boundary. M is at least this, where A is the area of any component in the boundary. Any component in of the boundary. And equality holds, again, equality only if M is isometric to the half Schwarzschild. Okay, so let me say a few words about this. Right, so let me say a few words about this. first of all, so this was proved around the year 2000, right? And there are actually two proofs. One of them is actually stronger than the other, but I'm going to talk about the, at least with respect to the statement, weaker version, because it uses the inverse curvature flow that will be important in the next talk. So, but I have to say the following. So, Huysken and Ilmanen gave a proof. They're both of the year 2001. Proof of that statement using inverse mean curvature flow. Inverse mean curvature flow. And the good aspect of this, although it's weaker, is that it's independent of, well, let me put it this way, reproves the positive mass theorem. And as I said, Bray, around the same year, gave another proof which is stronger because he proved that actually this holds for the whole area, the sum of the areas of all the components. So he holds the case of n equals to the whole boundary, right, which is stronger, using the conformal flow. But the proof uses the positive mass theorem. So just to point out that we actually know more, that we can put the whole area here, but I'm going to give the proof of the uses the inverse mean curvature flow because it's more suited to the mini course. So that's what we want to talk about. So why do we need, okay, so this boundary has to be a minimal surface, but why do we need the condition that M contains no other minimal surface? Well, because there's a counterexample if we don't ask for that. Counterexample is very simple to construct. The idea is the following. You take any, you can start with, for example, R3 with any asymptotically flat manifold, right? Let me put this like this. You choose any asymptotically flat manifold with no negative scalar curvature, but such that the scalar curvature is strictly positive at some point. Right? Let's say this P is a point where the scalar curvature is positive. You can easily do this by conformal deformations. So it comes with the mass, it has some fixed mass M, but there's a little region here where the scalar curvature is positive. Once you get a little, once you get positive scalar curvature, you can do connected sums. So you can come with, you can bring, like, for example, round sphere here, which has positive scalar curvature. And there is a way of joining these two by a neck. You can erase a small ball here and glue a small neck so that the resulting manifold has positive scalar curvature. Right? And you can continue doing this. You can do a connected sum, let's say, with an even bigger sphere. So you can see this is a minimal surface with area which can be chosen to be much bigger than the mass, right? Well, much bigger than m squared. So if I choose my manifold to be this, I would have a counterexample. Of course, this is not really a counterexample because this is not the right minimal surface. Once you have a region like this, you have to sort of like look at the most exterior region possible, and the right minimal surface would be something like this. This would be the right end. And for that, the theorem is true. Right? So the theorem doesn't hold for any minimal surface, but it holds for the, let's say, the outermost one. So that's why one needs this condition. And actually, it appears, sort of appears in the proof as well. Okay. So why is this related to flows, right? Well, the point is that there is a very nice monotonicity formula. Actually, in some sense, almost everything I'm going to talk about here is going to be related to monotonicity formulas. Monotonicity formulas are very important in geometry, as we know. So it's based on the following definition. So suppose that N2 contained in M3 is a surface, compact surface. Then you say that the Hawking mass of sigma is defined is the following number. Oh, this is square root of the area. Oh, I'm confusing n with sigma here. So this will be my symbol for the area of the minimal surface. There is a constant here, which I always forget. It's 16 pi to the 3/2 and times 16 pi minus the integral of h squared. Right, this is the definition. So given a surface, you can define the Hawking mass, which is defined as this. Right. You can see from sort of like the, if you look at a round sphere, for example, in R3, you easily get that the Hawking mass is 0. Right? Just give some examples. The Hawking mass of a round sphere in R3 is 0. But actually you can prove more. You can prove that the Hawking mass of any surface in R3, compact surface in R3, is non-negative. Right? Well, at least a round sphere because this integral of h squared will be at most 16 pi. Right? Well, at least 16 pi. So actually, I get the wrong sign here. So what I'm saying is that if n is a sphere, suppose that n is a sphere, topologically a sphere in R3, you can just use Gauss-Bonnet to prove that the integral of h squared, h here is, I'm not normalizing, is the whole thing, will be greater than or equal to 16 pi over n. It's possible to prove this even for a surface of different genus. So I got the wrong sign here. The Hawking mass is actually negative. For any compact surface in R3. Right. And then an exercise here. Exercise. The first exercise is to prove that if you have an asymptotically flat manifold and you choose a system of coordinates at infinity, and then if you look at a very large sphere in that system of coordinates, the limit of the Hawking mass is exactly the ADM mass as I defined in the beginning. So the limit as r goes to infinity of the Hawking mass of this is equal to the ADM mass. Here I'm working with an asymptotically flat manifold. You have to just sort of expand the metric as a look at the Taylor expansion of the metric, and you see that the leading order term will exactly be the ADM mass. And the second very easy exercise is just to check that in the Schwarzschild manifold, the Hawking mass of the leaves is constant. This guy contained in the Schwarzschild example is equal to m for every r. Right? So the Hawking mass is actually constant in the Schwarzschild manifold. Okay, so now we're ready to introduce the flows. So in general relativity, this is actually noticed by physicists, right? Garak was the first one to notice that the Hawking mass is monotone under a flow called the inverse mean curvature flow. And that's the basic fact behind the whole strategy of the proof. So let me give the definition of the flow. Let me concentrate on the smooth case. So suppose that, I'll put it like this. We say that a smooth one-parameter family of surfaces, let me put it this way, x n cross 0t inside the manifold M. Let's assume that the mean curvature is positive because I'm going to, so far, talk about the smooth case. So we say that a family of surfaces is a solution, is a classical solution to the inverse mean curvature flow. Inverse mean curvature flow, which I'm going to abbreviate as IMCF, if dx dt is given by minus 1 over h times nu. So here h is the mean curvature how should I put this? H is the trace of minus the derivative of nu, just to fix the convention. So h is the mean curvature with respect to nu. If you think of a round sphere in R3, the mean curvature will be positive, right? Nu will be the inward normal. So actually this actually flows the surface outward. So it's an expanding flow instead of a contracting one. You probably have heard of the mean curvature flow, which you just take dx dt to be plus h times nu. This is a lot of people have studied that, but it's kind of funny that it seems that the inverse mean curvature flow has more applications to geometry than, when I say applications, I mean outside the flow business. Mean curvature flow has not that many applications to geometry so far, but the inverse mean curvature flow does. As I said, it's also the main tool used by Bray and Neves to compute the Yamabe invariant of RP3. Okay, so this is the flow. I think I can erase this statement, right? And what's the relation between these two things, these two problems? Well, the relation was noticed by Garock. This is called the Garock monotonicity. So he observed that, and we're going to do this calculation. He observed that if the scalar curvature is non-negative, right, then, and let's say if n is connected, the surface is connected, then the Hawking mass of the surface nt, suppose that nt here is just x of nt, right? Suppose that nt solves the inverse mean curvature flow. I'm going to put a star here. Solves star. Then the Hawking mass is actually non-decreasing. Along the inverse mean curvature flow. So the Hawking mass tends to increase. That's the basic observation due to Garock. And you sort of expect that this surface will expand, and you sort of expect that at infinity this nt will be very close to a coordinate sphere. So in that case, you expect that the Hawking mass of the surface will be very close to the ADM mass. On the other hand, a simple remark says that if the surface is minimal, right, if the mean curvature is 0, just look at the definition of the Hawking mass. This is 0, then you get 16 pi to the 1/2 actually. So this, in that case, the Hawking mass of n is exactly the square root of the area divided by 16 pi for a minimal surface. So that's the idea. You have your manifold which has a boundary formed by minimal surfaces. You choose one of them, and then you try to evolve the surface by inverse mean curvature flow, so that in the limit it converges to a round sphere. So if you're able to do this, because of the monotonicity of Garock, you see that the ADM mass has to be greater than or equal to the Hawking mass of the initial surface, which is just the square root of the area divided by 16 pi. And that's the strategy of the proof. Okay, are there any questions so far? Yeah. Oh, the integral of the scalar curvature is used so that the mass is well defined. Only that. Yeah, if the integral is finite, then the mass is well defined. Because the mass is a limit of integrals, right? So you have to prove that these limits converge. So the idea is that you fix a domain, fixed for forever, then you look at these domains which are bigger and bigger, and then you sort of try to do integration by parts. So when you do integration by parts, appears an interior term, which is the integral of the scalar curvature. So if that is finite, you get the limits converge, more or less. That's the idea. Okay, so this is the flow, this is the Garock monotonicity, and this is a mini course, so I'm supposed to do some calculations. Let's see why this is monotone. So this observation. So actually, the observation that it's monotone is due to Garock, and if I remember correctly, Jang and Wald observed that this could be used to prove the Penrose conjecture. No, this idea of flow in the minimal surface. But the problem is that there are lots of technical questions, technical issues, and those were only solved by Huisken and Newman in 2001. So you have to develop a weak formulation of the flow and prove that it does everything that you want. But anyway, let's just derive some properties of some calculations for this flow. Oh, the simplest one is to compute how the area evolves, right? But the formula is very simple. The derivative. So I'm assuming here that NT solves inverse mean curvature flow. So we have the dxt is minus 1 over h times nu. So the derivative of the volume element, right? Well, this is a normal variation, right? So it follows from the standard formula. This is going to be minus the scalar product of the velocity vector and the mean curvature vector times dv, right? This is a very standard formula. But if you do then the calculation, you get, or you have a minus here, a minus there. So you get 1 over h times nu, h nu. The mean curvature cancels, and you get the volume element. So this has the following interesting consequence, very simple, that if you integrate the volume element, you get the area, but then because of this, the derivative of the area of NT is equal to the area itself. In other words, the area grows exponentially. The area of NT is equal to the area of the initial surface times the exponential of t. Right? So the surfaces expand and the area grows exponentially. That's the first calculation. Well, now we have to differentiate the mean curvature. What happens to the mean curvature? Well, let's say that I'm going to denote by v the velocity vector, which is just dx dt. Scalar product with nu, this is the velocity of the flow. Then it's a very standard formula that the variation of the mean curvature is given by the Laplacian of v plus the norm of the second fundamental form square plus Ricci nu times v. This is the second fundamental form. Here I warn you that my Laplacian is minus the Laplacian used by Zindine. Otherwise I can get confused. But then if you do the calculation, if you suppose this is a general formula in general, but if you are working with the inverse mean curvature flow, you'll get the Laplacian applied to, let's see, dx dt is minus 1 over h times nu. So this is actually minus 1 over h. Minus a square over h minus Ricci nu over h. So this is the equation, right? So if you work a little more, you compute in this, you see when you differentiate this guy 2 times, what you get. This is minus h to the minus 1. So if you differentiate 1 time, you get h to the minus 2 gradient of h. Then if you compute the divergence, you get h minus 2 the Laplacian of h. Right? This is the first term. Minus 2 times h to the minus 3 gradient of h square. So minus 2 times this guy, h cubed, and the other guys, h nu divided by h. So this is the equation for the mean curvature. This equation is actually good in some sense, because if you apply the maximum principle, let's say we are interested in the maximum value of the mean curvature. So the Laplacian will be negative there. This is a critical point. You get a minus here. So actually this minus helps a lot in the regularity theory for the flow, which I'm not going to discuss here. But anyway, this is an important sign. If you do the if you do the mean curvature flow, you get the opposite sign. And the Ricci curvature term, remember that we are dealing with asymptotically flat manifolds. So the manifold is almost flat at infinity. Everything is going on in a complex set. The Ricci curvature is bounded. So this term is going to be bounded. So if you work instead of h, if you work with h square, right, this is going to be a bounded term, and then you can apply the maximum principle. So you get, if you look at the derivative of maximum of h square, this is going to be less than or equal to some constant coming from this guy. And coming from this, you use the Cauchy-Schwarz inequality. You use that a square is greater than or equal to h squared divided by 2 in this case. Right? So you get minus h squared, maximum of h squared divided by 2. Right? And then it's very easy to see that if the mean curvature is very large, right, the right-hand side here is going to be negative. So it's saying that when the mean curvature is large, it tends to go down. So when you apply the maximum principle, the corollary of that is that the mean curvature has to be always below some constant here. So, sorry?
The other inequality for a squared, less than or equal to a squared.
No, because so a square here is, let's say, lambda 1 square plus lambda 2 square. That's my definition of a square. Right? And so this would be this, and the mean curvature is the sum, right? Square divided by 2, right? So I guess you'll get the right sign, right? You get probably 1/2 of this, right? Okay. So the corollary of this is that the mean curvature is bounded. H is less than or equal to C. This is very different from what happens in mean curvature flow. Mean curvature flow, things tend to contract, and mean curvature tends to go to infinity. Inverse mean curvature flow is the opposite. Surface expands, mean curvature is always bounded, but then the problem is, well, one of the problems is that the mean curvature could go down to 0. Mean curvature going down to 0, you get a singularity of the flow. And you can sort of see that could happen. There's an example of a torus in R3 in which you can see that this happens. I don't know if I will be able to make a picture here, but sort of the idea is that if you look at a small torus of revolution, right? You can choose it so thin so that the mean curvature is positive. So the inverse mean curvature flow will make sense. This torus will expand. This is saying that the mean curvature is bounded by C, but the velocity is actually 1/h, right? So it implies that the velocity is at least 1/c, right? So it moves fast. It never goes slow. So sort of, sorry about the picture, it's very bad, but the idea is that this expands with a speed bounded from below. So at some point we'll develop negative mean curvature or 0 mean curvature. So at that point the flow stops. So you can sort of see that these kinds of singularities can actually happen. Okay? Right. I have to go fast. Anyway, we can sort of like, let's look at the calculation then. Now we want to differentiate the Hawking mass. Remember that the Hawking mass of n is defined to be the square root of the area divided by some constant times 16 pi minus the integral of h squared, the volume element. Let's do the calculation now. So suppose this is evolving by inverse mean curvature flow, and then we want to differentiate. I have to do this because I want to derive a formula, actually. It's not just the fact that it's non-negative, but there's actually a formula. So if you compute the first derivative of this guy, maybe before I do this, let me just comment that this is a parabolic flow, right? This is important. This is a flow, a partial differential equation. So why can you solve the flow, right? Well, the idea is that because of this minus, if you think of the linearization of minus 1/h, right? This is h to the minus 1, so this is basically h to the minus 2, the linearization of h. Right? The mean curvature flow, remember, is parabolic. And so now the linearization is just the linearization of mean curvature times something positive. So again, this guy is parabolic. Okay? So that's why the minus sign here. So given a surface of positive mean curvature, in general, you cannot solve it inside, but you can always solve it outside because of the parabolic nature. This is a parabolic flow. Okay, so let's go back here. So let's look at the derivative here. First we have to differentiate area, but that we already did, right? So the derivative of area is going to be 1/2 of area to the minus 1/2 times the derivative of area, which is the area itself, right? So you get a plus 1/2 here, divided by this constant times 16 pi minus this. Now I have to differentiate inside. So I repeat here the area divided by 16 pi to the 3/2. So when I differentiate inside, the constant cancels, and I get minus, let's see, 2 times the integral of h dh dt. Right, that's one of the terms. But now I have to differentiate the volume element as well. Then I get minus h squared, and remember the derivative of the volume element is the volume element itself. So that's the formula that I get. Let me concentrate on this guy, and then later I'll get them together. So if I look at minus 2 integral of h dh dt, I will get, well, dh dt I have computed here. So let's see. So let me use this. Okay, the Laplacian of minus 1 over h minus a squared divided by h and minus Ricci divided by h. Is that correct? So that's the formula. So now the first guy I can integrate by parts here, right? So I get minus with this plus, but then when I integrate by parts I get a minus again, twice, and gradient of h, gradient of 1 over h. That's the first term. The second term, observe that h cancels. So we get the integral of twice a squared plus twice Ricci. So that's the formula. This we can look at the gradient of 1 over h, which is just minus gradient of h divided by h squared, right? Then I get a plus 2 with this minus here of gradient of h squared divided by h squared. And then I just repeat this other term. Okay, this is very good. Now I have to put these terms together, use Gauss equation, and in the end, when you use Gauss equation, of course, the Gauss curvature will appear, and then you want to use Gauss-Bonnet. Right? So you have the inverse curvature flow. The Hawking mass is defined in such a way that when you differentiate that with respect to inverse curvature flow, the h's cancel, and you're left with exactly the Gauss curvature. Right. So let's do this calculation here. So I'm sort of finished. Today I'll finish the smooth case, and in the beginning of next talk, I will summarize the weak version. Okay, so let's finish this formula. Let's put the results together. So the first derivative of the Hawking mass of nt is going to be, let's see, 1/2. I'm going to put the area outside divided by this constant, right? And then I get a 1/2 here, which gives me 8 pi minus 1/2 integral of h squared, right? From here, from this guy I have exactly minus integral of h squared. I hope this is correct. And now I have this guy here. So this guy here gives me this. So I got plus twice gradient of h squared divided by h squared plus twice a squared plus twice Ricci. Okay, that's the formula. Now the Gauss equation, the Gauss equation after you contract gives you the following, that the scalar curvature of the ambient manifold is equal to twice the Ricci curvature plus twice the Gauss curvature of the surface plus norm of a squared minus h squared. That's the Gauss formula. So then, if we use that here, you get the area to the power 1/2 divided by this constant. Okay, let's see. So now we get minus 3/2 of integral of h squared. We have that guy over there. This guy is good because it's positive. Twice a squared. So now I'm going to substitute Ricci curvature. So twice the Ricci curvature will give me the integral of the scalar curvature, then minus twice the integral of the Gauss curvature, minus integral of a squared, and plus integral of h squared. Is this correct? I hope so. So finally, collecting the terms together, we get the following formula. So that's actually the Garrock formula. Right? Or if you want, Garrock monotonicity formula. Monotonicity formula. That the first derivative of the Hawking mass of the surface is going to be equal to the square root of the area divided by this constant times I have this guy here twice gradient of h squared divided by h squared over n. Let's see. So now I have 8 pi minus twice the integral of the Gauss curvature. So by Gauss-Bonnet, the integral of Gauss curvature is equal to 2 pi times the Euler characteristic. So these terms together give me 8 pi minus the Euler characteristic of n. Right? These two guys here. Sorry, not 4 pi, the Euler characteristic. And here I get minus 3/2 with 1 minus 1/2. 2 minus 1, I get 1. So I get exactly plus the integral of a squared minus 1/2 of h squared. And I got rid of all these terms here. And also this, and there's left the integral of scalar curvature. Plus integral of scalar curvature. And that's it. That's the formula. So as you can see, this the calculation here, right? The bound says that this term is also always non-negative. This is actually equal to the norm of the trace-free second fundamental form. So this guy is non-negative. This guy is also non-negative, right? I'm going to assume that the scalar curvature is non-negative, so this guy is also non-negative. And for this, I need n to be connected. Right? If n is connected, I know that the Euler characteristic of n is at most 2. Right? So again, this guy is non-negative. So the corollary is under the conditions of the surface is connected and the scalar curvature is non-negative, the Hawking mass is actually non-decreasing with time. That's the formula. Okay. So the idea, as I said, I have 10 minutes left. Let me just prove, sort of sketch the proof if we had a smooth flow. And in the next talk, I will briefly summarize what Huisken and Newman had to do in order to really come up with a weak flow for the setting. So the idea is that you have this manifold, right? Let me talk about just one component. This guy is a minimal surface. And then you sort of want to find a flow which becomes immediately of positive mean curvature, and such that it evolves under the inverse mean curvature flow, and at infinity looks almost like a coordinate sphere, almost like a boundary. So then this is inverse mean curvature flow, foliating your manifold. Because the Hawking mass is non-decreasing, you get that the Hawking mass, that the limit of the Hawking mass as t goes to infinity, which is going to give me, this is just a sketch, right? The ADM mass, well, because it's a non-decreasing function, this is going to be greater than or equal to the Hawking mass of the initial surface, but the initial surface is minimal. This is just square root of area divided by 16 pi. So that's the strategy for the conjecture. So what about the case of equality? Let me finish with that. The case of equality also follows from the monotonicity formula. So suppose equality. Suppose that the Hawking mass, that the ADA mass is equal to the square root of area divided by 16 pi. So you have equality there. In other words, the Hawking mass of the surfaces have to be constant. Right? And also, all these integrals have to be 0 in order for you to have equality. So this has to be 0. This implies that the Hawking mass of nt is constant. So it implies that the right-hand side is 0. But all of them have signs, so we can see, for example, that gradient of h is 0. Right. Gradient of h is 0. In other words, h is constant. In constant as a spatially. Right? I'm fixing nt here. I'm picking an x and nt. So it's the surfaces will have constant mean curvature, first of all. The Euler characteristic has to be 2, right? So they have to be spheres. So the Euler characteristic is 2. So n is a sphere. What else? The surface has to be umbilic, right? Because the trace-free second fundamental form is 0. So they are umbilic. A0 is 0. So n is umbilic. And the scalar curvature has to be 0. Right? So m is scalar flat. So I want to prove that the manifold is actually Schwarzschild from that. So what do I do? Well, the idea is that we have almost everything. Let's see, I erased the equation for the mean curvature. Let me copy it here. Remember that the derivative of the mean curvature was given by Laplacian of minus 1 over h minus a square plus Ricci nu divided by h. Right? So the fact that h is constant, if you look at this equation, if h is constant, well, constant is spatially, right? Spatial constant. Then, of course, the derivative with respect to t has to be a spatial constant as well, right? This will be a spatial constant. So this guy is going to be constant on the surfaces, on the levels, on the leaves, right? This guy is 0 because it's a Laplacian of a constant. A square, we we already saw that this is going to be a constant because the trace-free part is 0. So all you get left is the mean curvature. So from the equation, you get that the Ricci curvature is constant. Right? Ricci nu is also a spatial constant. So now the Gauss equation, you look at the Gauss equation, you know that this is 0, this is a spatial constant, this is also a spatial constant, the Gauss curvature is constant. Right? Applies to the Gauss curvature is constant. In other words, all the leaves are round. They have constant curvature, isometric to round spheres. So let me finish then the proof of the equality case. So this is all of the information that we need. So you have this surface nt, which is evolving in time. So I'm going to the velocity vector, in other words, the ddt, is exactly as I defined, minus 1 over h times the normal vector. So if I use dt as a coordinate, my metric is going to be written as the metric applied to the ddt direction will give me 1 over h squared. Right, so 1 over h squared times dt2 plus, then I have the metric on the surface, but the metric on the surface is isometric to round spheres, so I'm going to write this as r squared of t times ds2, where this guy has constant curvature. Right, so that's the expression of the metric, and then it's now just a matter of computing all these things. Right? For example, the area of the surface, you can compute it in two ways. Right? The area of nt in this formula here is going to be 4 pi times r squared, but this is also equal to the area of the initial surface times exponential of t. So my goal here is just to write it in terms of r, right? So if you look at this expression, you get that at this equality here, you get that exponential of t is equal to 4 pi divided by this times I squared. Then t is equal to, you take the log, right? Twice log of r plus the log of this constant. So this is a calculation of a physicist. Right? Sorry about that. You differentiate this, you get a dt is going to be twice dr over r. Then you just have to replace, let me not erase this. Once you erase that, you get that the metric is 1 over h squared dt squared. So dt squared is just 4 dr squared over r squared. Plus r squared ds2. So let me just, I'm sort of tired, so let me just write the final expression. Now it's just left to compute the mean curvature. But then you compute the mean curvature because you know that the Hawking mass is constant, right? So you know that this expression, square root of the area divided by the constant 16 pi minus this is equal to a constant. So you can we already know the area. One can compute the mean curvature from that. You get that the mean curvature is equal to h squared is going to be equal to this. And then we're finished. Because in the end, the metric will be in a slightly different form of the definition that I gave, but it's actually the same manifold. Right? So this is the Schwartz geometric. So the key is really the Garak monotonicity formula. Of course, I'm cheating a little bit because I'm supposing that that the flow is smooth and everything converges, right? As I said, there's a whole theory developed by Huisken and Ilmanen to develop a weak mean curvature flow. And what I'll do is that in the next talk, maybe the 20 or 31st minutes, I will summarize the theory before going to the Yamabe invariance of P3. Okay, so I'll stop here.